Swayam Prabha. Digital India. Educated India.
So last class we started with our CTMC study, and we kind of defined the notion that the sojourn times, that how much time my CTMC is going to stay in a state, I'll continue to stay in a state before it leaves it. And in the last class we showed that has a exponentially distributed, it is exponentially distributed with a parameter AI. That AI is state specific, the I, whichever state you started looking at, and the time after which it has left that state. So basically it is, we had this random variable so we said that yt is the time, remaining time after which you will leave the current state, okay. And then we had said that, okay, suppose if I conditioned this random variable knowing that at time t I am in that state I. So here in this definition, yeah, what is that? So here when I defined this is not state specific. I just looked at, okay, I start looking my CTMC at time t and just see what is the minimum time before it leaves my current state. And here suppose if I condition that, okay, when you start looking at your CTMC, you are in a particular state I, and then how much, what is the probability that it is going to take at least u more units of time before you are going to leave. We had shown that this to be e to the power ai of u for some ai which we say can be between 0 to infinity. Okay, let's say I have this random variable. So yt is a random variable here, right? Suppose I condition this random variable like here, I xt I equals to 0, or let's say more generally instead of particular t I am going to look at times equals to 0. So I am saying that in the beginning at the 0th instant I am in state I, and then I am looking at 0th instant I am in state I, and then I am looking at when is that I am going to leave my state, how long I am going to stay. So what is this y naught is going to give you? What in this case, what will be the distribution of y naught? It is basically the first time you are going to leave out of state I, right? So you are saying I am going to start from state I. Y0 is nothing but the minimum time when you are in a state which is different from I. That is basically, in a way, it is going to say when is that your state is changing. In a way, this is same as like our random variable t1, right? So you remember how you define t1? T1 is the instances at which the renewals were happening. Here, if you are going to interpret, your renewals are when you are going to change your state, right? Then t1 is the time here, that is given by this random variable y of 0 condition that. So this is t1 is the basically the time that you are going to leave state I here, because I have conditioned on I here. Okay, fine. So now you see that the amount of time you are going to stay or the rate at which you are going to transit to other states is going to be governed by this parameter AI here, right? So based on that, how this value of AI is, then we can classify the states in my CTMC, right? So let's see this. What are the possible things we can get? See, like the sequence of random variables, sometimes I write it x of t like this, sometimes I simply write like subscript by t, like we'll assume that both are indicating the same. Okay, and a state I is called So I have classified them into two things. So if it takes the value at the boundaries, either if it takes the value 0 or infinity, then we are going to either call them absorbing or instantaneous. Specifically when it is going to take value AI equals to 0, we are going to call it absorbing, and when AI equals to infinity, we are going to call it instantaneous. So let's see this. Suppose AI equals to 0. What is this telling you? AI equals to 0. It is basically telling you that anyway this probability. So if AI equals to 0, whatever you are going to take, this is going to be 0, right? Sorry, this is going to be 1. So however large u is, however large you are going to take, it is still going to be 1. That is probability that your yt is going to be larger than that quantity, that is you continue to stay in that, however large u, it is going to be 1. Then that makes sense, like that's why you are going to call it absorbing. That it is basically got stuck in that whichever you started with, that it's basically never living. How far you are going to look, it has been. And now suppose you put AI equals to infinity now. Now if put AI equals to infinity, for whatever value of small u, this guy is going to be 0, right? So however small value of u we are going to looking that your Markov chain is going to stay in that state is just 0. You put u arbitrarily close to 0. Once AI is infinity, this probability is going to be 0. That means there is no way like my Markov chain is staying in that, continuing to stay in that change. It is just like as soon as it leaves, it is leaving that instantaneously. That is because however close u is close to 0, this probability is 0. That is the reason when AI equals to infinity, we are going to call it absorbing. Now anything in between this, sorry, instantaneous, we are going to call it instantaneous. And anything in between this, when AI is strictly away from infinity or like strictly finite and it's a non-zero quantity, then we are going to call it as stable case. Okay. So now see, like in our DTMC, we had a classification of our states into, there also we had transient, recurrent, right? recurrent, further null recurrent, positive recurrent. There also we have the notion of absorbing state. But here we have another classification of states when it comes to CTMC, that is in terms of whether how that parameter AI associated with state is going to be, whether it's 0, infinity, or something in between these two. So we are going to call so basically now we are going to focus on a CTMC in which the states are slightly well behaved. Like my CTMC is not like which is changing very fast, like instantaneously, right? Like that means it's a kind of highly unstable scenario, right? Like every instance your CTMC is taking different states. So I don't want to have such case. So henceforth I am restricting to CTMCs in which such states does not arise. So is this clear? We are just going to say that like in a way my CTMC is well behaved, like it is not going to change its state at a very high rate. It will change its state, but at some bounded rate. So like in this case, when it is observing, once it hits the state I, it is not at all changing its state. Here the rate of change is 0. But whereas in this case it is still changing its state, but at some bounded rate. But where in this case it is changing its states at a very unbounded rates. If you hit a particular states where AI equals to infinity. So we are assuming that my CTMC does not have such a states. Okay. Okay. Next we are going to focus on so now we are going to study how does this CTMCs, which are pure jump structure, they are going to look like. What are the things I need to characterize them? Okay. See, like in DTMC, we always looked my Markov chains to a time index, which was kind of discretized, and we know that okay, at some discrete times we were looking at. Here, that time itself is a random quantity. So suppose in a discrete time Markov chain, you looked at T1, T2, let's say at periodic time, not necessarily periodic, but at some discrete times. But now when you are going to look at the CTMCs, an event is happening at some times, right? And these times are random. Okay? So the jump is happening at some time, next jump is happening another time. So, and if you are going to focus on this events when the state is changing, and you are not interested something in between, right? As long as my CTMC continues to stay in a particular state, fine. But when it changes, that is the event of maybe of interest to you, and that is happening at random times. So often in this case we have to condition on random times, and naturally we will be asking the same question as we asked in DTMC, that is my CTMC satisfies a strong Markov property, right? So in DTMC we also looked at when we condition on random times whether it still satisfy Markov property. If it dissatisfy, then we call it as a strong Markov property. So we want to see similar thing holds here. So for that, first we are going to define what is a stopping time for a CTMC. So this definition is exactly same as that in DTMC. We just want to know that if there exists a function f such that if I want to answer the question that my random variable t is going to be less than or equals to t, I only need to look at my random process up to time t, nothing beyond it. If this is going to happen, then we are going to call that time t as my stopping time. Now let's say Tn to be the instance of nth jump. See, I am using the terminology jump here. That means that at this time my Markov chain is changing its state, right? It is leaving its current state and going to something else. That is what I am calling it as jump. Now let's say Tn is the instance at which my Markov chain is changing its state for the nth time. Is Tn a stopping time? Right. So if I need to know whether my nth jump has happened till time before time t, you just look at your Markov chain till time t and see how many times it has changed the state, and you can know this answer. So you can always have such a function f here which will say yes or no. So Tn in here happens to be a stopping time. And you can also see that if your random time t happens to be just some given t, then also it is a stopping time, as we did it in the DTMC case. So okay, now with this we are just going to define our strong Markov property like we did in our DTMC, which is as follows. Okay, so what we are saying, we are just saying that okay, if t is a stopping time, if you are given your you have observed all your CTMC till that time t is this stopping time, and then you are looking at your Markov chains taking the value I1 after T1 rounds and I2 after further T2 rounds, like this. If this is going to be like as if I start looking my Markov chain from the beginning. It is as if I start my Markov chain from state 0, where it has taken state I0 and subsequently it has taken state I1 at time T1 and IN at time T1. It is just like at random time, whenever it is happened, I am just pushing it to the origin and then I am pretending as if I am looking my Markov chain from the origin. Okay, so if you are going to condition on a Markov chain, that's fine, like as long as that is going to be a stopping time with respect to that Markov chain, it's good, like you can pretend as if you are starting from the beginning. Okay, fine. So this is the definition of a strong Markov property we are going to assume. Now, you see that even though my time is continuous, I am basically looking at discrete events, right? I am going to, because I have focusing on my pure jump CTMC here, I am going to look at the events where my state is changing. So these are like discrete events because the things are not happening instantaneously, they are happening after some time, and this time is positive with probability 1. So you are going to see kind of events that can be possibly indexed with discrete indices. So for example, first transition, second transition, third transition, they could be happening at different random times, but still these events you are indexing by discrete numbers, right, like 1, 2, 3, and they are all you can make a countable indices set. So based on this, we can, out of my continuous time Markov chain, I can extract an underlying embedded chain. Okay, so let's see what is that. So I'm going to assume like Tn, this sequence is what is my nth jump. This is the sequence of jumps. Now I have my continuous process xt, right? Now this process I'm going to sample at this sequence, this random times. So let's say now I'm going to get or maybe like, okay, fine. From this I'm now going to define xn to be x of tn, and now I'm going to look at this sequence xn and I'm going to call this sequence as an Tn is the no xt is your process, right, continuous time Markov chain. It is just like you set t equals to Tn, right, exactly. So you are, let's say if you are going to if you are looking at your CTMC as a function of time, you, let's say initially you started, let's say for simplicity, you from state 0, let's say you are going to stay here till this point. Let me call that realization T1, which is the realization of my random variable T1, and after that you have jumped for time being, let's assume it's a counting process, so you have taken a value of 1 here, and after that you will make this sometime here, then go here, maybe take a long time here, and then make another jump and like this. Okay, so these are all your samples, T2 and like this. Once you tell me these realizations, I am going to sample this process and I am going to derive. So in the counting process, it so happens that like every time there is a triggered, we are always counting 1 and it is going 1, but it need not be always the counting process, right? It could be something else. For example, it is transiting to some arbitrary states. So in that case, this could be something like these are different states you are going to transit, and that is captured by this jump process, xn. So this is a kind of an embedded discrete time process which is embedded in my continuous time Markov chain, right? So this is an embedded process, and we are going to call it as a basically a jump chain here. Whether it's the DTMC, we will see that. If we have a chain now which is discretely indexed, what are its properties and how this is looking at the properties of this jump process, we can say something about the properties of the CTMC is what we are going to study next. It will not make an assumption like here in this particular case, like whatever, let's say if it is not right continuous, whatever the value of your xt at time t1, you are just defining that to be xn. So in this case, if it is right continuous, you have taken the jump, whatever the new value after the jump it is happening. Otherwise, you would have just taken this value. So be it, if we want to define it like this. So whatever that, we are just going to call it an xn sequence. Okay? Okay, fine. So next we are going to see that now I have a jump sequence here which is discretely indexed, and let's say this is now defined on the same state space, on state space. So my initially state CTMC is defined on state space S, my jump chain is also defined on the same state space. Okay. Now let's say that on this I want to define a transition probability method. Okay. So how can I do that possibly? Because let's say here also like what? I can ask the question, okay, initially, so now I have basically this chain xn. I can ask, okay, what is the probability that this chain takes value j given that it has started from a particular state? Okay, that you can always ask this question, right? Like what is the probability that in one step it takes a particular. So suppose let's say on this state I could always ask, like if I and j belong to my state space, I want to ask this question, okay, what is this probability? What is this probability? This probability could be simply, let's say, probability that my x1 equals to j given my x0 equals to I, like we did it in the DTMC. Okay, so fine, but I have not started with this. I have started with my CTMC, for which I know P of t, right? What is P of t? Yeah, for every t it is going to give you the matrix, right? For your original CTMC. So fine, how you are going to define it in terms of my initial P of t? See, like going from state x0 to x1, this is happening in how much time? According to my initial CTMC, t1 rounds, right? Now basically what I am asking this question is probability that x of t1 is equals to j given that x of 0 is I. Right? Now this was like an embedded process, but now I have written in terms of my continuous process, Now I can write using my PT, I could find out what is this probability, right? So depending on how your distribution, what is the distribution of this T1 and what is the corresponding values of matrix PT, you can go and compute this value. Okay, fine.